Next presentation is also from Europe, maybe actually from China, I don't know, because it comes from SynSense, and SynSense has offices both in Switzerland and in China. So the title of this presentation, Efficient Inference of Low Resolution Optic Flow on Low Power Neuromorphic Hardware. And the presentation will be given by Felix BAUER, and I think we'll figure out soon if it's China or Switzerland. Okay, let's start.
Hello everyone, my name is Felix BAUER. I'm a research and development engineer at SynSense, where we develop neuromorphic hardware and algorithms for low-power AI applications. In this talk, I will explain how we perform motion sensing for drones in real time at low power consumption. For navigating a drone, information about how it is moving is essential. This is commonly done by using inertial measurement units or IMUs. However, there are situations where this type of sensor is not very precise. For example, when the drone is trying to hover in a fixed position, it can happen that it slowly drifts off, maybe due to wind, and that this is not being registered by the IMU. Motion can also be inferred visually, which is less prone to this issue. Visual motion inference can therefore be a viable alternative or extension to IMUs, in particular during hovering or landing. Here at SynSense, we have developed the Speck Smart Vision System on Chip, which comes in very handy for this task. It consists of an event-based vision sensor that directly feeds into an asynchronous spiking CNN processor. On the right-hand side of the slide, we see the whole packaging with lens, and as you see, it is very compact and therefore easily fits even into small devices. To the left, we get a view inside the packaging where we can see the actual chip. But what is event-based vision? Different to usual cameras, event-based vision sensors work asynchronously. That means that instead of producing frames at a fixed rate, each pixel produces an event as soon as the measured brightness changes by a given value. You can see how this looks like here on the right of the video, compared to what we would see through a standard camera on the left. Note here that when nothing is changing in the visual scene, no events are produced. This form of sensing allows low latencies and, together with our asynchronous processor, sparse and power-efficient computation. On the bottom there is a sketch of the processing architecture. Input events can be fed through up to 9 spiking CNN layers with configurable stride, kernel and pooling, as well as a dense layer. This chip is not limited to motion inference, but can also be used for any other vision-based application. In order to perform visual motion sensing, we designed a spiking CNN model that receives events from the vision sensor. An example for such data is given to the left. Here we see events that have been recorded from a vision sensor mounted on a drone that was flying indoors. Based on this input, our model predicts a low-dimensional optical flow field in real time, as is shown on the right. Optical flow is the apparent motion in a visual scene and can be used to obtain ego motion information. In contrast to other solutions, in our model, processing of temporal features happens in a completely streaming fashion, without any buffering or framing of input data. The model is trained on a standard PC directly as a spiking neural network through backpropagation through time. We can then deploy the trained parameters onto the Speck chip. Here we see the model architecture. With 3 convolutional and 2 average pooling layers, the network is quite compact. Now let's take a look at how the model performs. We see here an animation of the input events, together with ground truth optical flow, indicated by green arrows, and the model predictions as blue arrows. As we can see, predictions match the ground truth very nicely. To conclude, we have seen that drone motion can be inferred in real time from event-based vision data by spiking CNN. Such a model can be implemented on low-power neuromorphic hardware such as SynSense Speck. Thank you very much for your attention. I would also like to thank my colleagues Nogai and Sadiq for their extensive collaboration on this project. Feel free to contact any of us for further details.
Thank you, Felix. Very interesting presentation. I have several questions and also from the audience. Let me start with my question number one, the mystery question. Are you based in Switzerland or are you based in China?
Thank you very much. In fact, I'm based in Zurich, Switzerland. But you're completely right. We also have offices in China.
Yeah, that's actually great to see this Asia-Europe connection at the company level. And thank you also joining for such early time for you. Really appreciate it. So another question, there is a question on the chat asking, what is the resolution of the sensor you used in this study?
The sensor we're using has a resolution of 128 by 128. And in fact, here we're cropping it even smaller to 64 by 64. The idea is to have a very low dimensional sparse signal and computation.
Got it. And talking about sparsity, I have a bit of a dilemma in my mind. Before we go there, definitely there is a problem statement with IMU drifts, like as you put it out at the beginning. And for this, that's the reason why cameras are used on drones for different type of things, for navigation, for the landing and this kind of things. But then the dilemma I have in my head is event-driven cameras actually work well when your data is sparse, right? When your image is sparse. And for event-driven camera on a drone, there is always motion. I mean, there are always pixel changing. What is the advantage of using, that's kind of a dilemma I have, what is the advantage of using event-driven camera versus standard camera in this type of scenario when your object moves constantly at high frame rates?
Yeah, that's a really good point. Obviously, it's much less sparse than when you have a static camera. It is, I would argue it is still sparser than frame-based, because in frame-based vision we have information at each pixel whether there is something or not. Whereas your drone-mounted camera, there might be areas where there is where there's constant brightness or color gradient, or the drone might not be moving for some time, and there then the sparsity argument comes in. Another advantage of event-based vision is that you can achieve lower latencies, because you're not restricted to the actual frame rate. So information basically passes through instantly as soon there is any motion onset.
Yeah. And related to latency, there is one more question. I noticed kind of on one of your last slides when you show the ground truth versus the calculated vectors, there was a little bit of a time lag between the two. So what is kind of the root cause of this? Is it because of the data transmission or compute? Or that's kind of question number one, what causes this lag? And question number two, in terms of kind of performance requirements for this drone type of application, is it good enough to have this kind of lag between the ground truth and the compute and the data? For example, if you're in a mission critical type of task like landing or whatever, and if you kind of have this little bit of a lag, is it a big problem? No problem at all. I mean, what is the requirement basically from the end use case?
Yeah. So first of all, this the lag that we see here we're still looking into that, but I would think it's from the simulation. So this is currently not a recording from the hardware itself. In more to answer this a bit more generally, if you run this on event-based hardware, the lag, when there is any, comes from the events passing through the network. So if you have a very low event rate in your network and a deep network, then it might take time for the information to pass through. So that this is it's a bit of a trade-off between accuracy and latency versus sparsity. So you can decrease latency by increasing effectively the number of events per time. As for the applications, that's actually something that we would like to try out. So unfortunately, I can't give you a definite answer. I'm pretty sure it depends on the actual implementation. So if the drone is moving very fast and has very brisk changes in motion, then yes, this might become more of an issue as to for example the case where it's just hovering and where reactions to any motion can don't have to be immediate. But this is something we would like to try with an actual drone.
Yeah, that will be interesting to understand. Yeah. And back to the resolution question, I think in this study you use more traditional, kind of, I would say, the classical 128 by 128 sensor. It's the kind of very, very famous one. And then recently we saw an announcement, and I think it's a public domain announcement, that SynSense had a partnership with Prophecy on kind of a high resolution sensor, which is actually, to me, is quite exciting because it combines kind of the two best worlds, your engine to do Speck and computing on the neural nets, and their pretty advanced camera they use. So can you comment on this and kind of what it means in terms of kind of use cases and what it means for new developments like what you showed today, and what it means to customers who may use this type of product in the future?
Yeah, so first of all, we're obviously very happy to collaborate with Prophecy. And yeah, for use cases, I would argue that in the drone case, we are probably fine with this resolution, but then there might be more static applications like gesture detection or movement classification in a broader visual scene where this higher resolution comes in handy.
Got it. Okay. Thank you. Let me check. We don't have more questions on chat and no more questions on Q&A. Well, thank you again, Felix. I think it's actually very good to follow the progress the company is making. I mean, the way gesture demo at the summit, and now the drone demo here. So I think looking forward to more progress, and we'll see you probably at the summit again in March.
Thank you very much.
Thank you. And thank you for joining us earlier again. I'm sure, again, the audience appreciate this.
Happy to be here.
Yeah, thank you.
Thank you to our strategic partners who supported us, especially some of the key partners here. We've got ARM, who help with hardware and software. The Tiny, what's called Edge Impulse for developers on the libraries. Qualcomm Advanced AI Research as well for their support in edge computing. Syntient around hardware and ML training pipelines. So definitely thank you as well. Platinum sponsors, Reality AI for advanced sensing with product and tinyML. Renesas for microcontrollers and microcomputers. Our gold sponsor, Sladen.ai, Adaptive AI for the Intelligent Edge. Maxim Integrated, enabling edge intelligent devices. Seed Hardware, who also had present today. I'll quickly go back to them. Thank you once again for all your support. SenseML, build smart IoT sensor devices for data. SynSense, and our silver sponsors. So thank you once again. It's been a great few days. Look forward to 2022, as mentioned before, and hopefully see you at some of the future tinyML events. Thank you.